Okay, so we're moving on from Lewis dot structures and visualizing molecules in 2 dimensions to starting to talk about molecules in 3 dimensions. We, by our nature, are 3 dimensions, and thus the molecules that make us up have to be 3 dimensions too. So before we talk about shapes, we need to understand this idea of an electron domain. And this is the space occupied by valence electrons in a molecule. It either counts as a bonded pair or pairs, or a lone pair. A double or triple bond counts only as one domain, and electron domains affect the overall shape of a molecule. I think of domains as, what color should I use? I'll use red. As sides covered by valence electrons. That's probably the way I'm going to describe it more simply. How many sides are covered in your Lewis dot structure, your structural formula, by valence electrons? And so we have this idea called electron domain theory. And there's this fancy name that you may hear, which is VESPER, which is valence shell electron pair repulsion theory. We'll just call it electron domain theory. And this goes back to your physics. This goes back to electrostatics. Remember early in the year, I told you how important electrostatics was for chemistry. So this is the idea that every domain in a molecule wants to be as far apart from every other domain in that molecule. So they're going to push. So the idea that every electron domain really, and this isn't quite right. This should be every domain around one atom in a around one atom. Because it's not the number of total domains in the molecule, it's the domains around the atom. As far as possible from other electron domain in that atom. All right, so you might want to pause here. I'm going to move forward and pause to take the notes. When you're ready, move on. Okay, so we saw this today. When you were doing your marshmallows and gumdrop activity, almost all of you started with this idea, one of these two ideas. I'll call it 1A and 1B. You either put them all 90 degrees apart first. That tended to be the one, but that's flat. That's 2 dimensions. And then you thought to yourself, oh, 3 dimensions. Well, I'll just move this one over, move this one so it's perpendicular. But again, you're all 90 degrees apart. So it turns out that there's a better way that you could maximize the space between them, and it's about 109.5 degrees. So all bond angles are the same. So they're either not equally distant, or if they are equally distant, they can be further apart from one another. So if you look at your marshmallow drawing, each one of these bonds represents a side, and that's an electron domain. And each of those sticks, if you think about them as a pair of valence electrons, they want to be as far apart from one another as possible. So hold on one second. I want to add a slide in here. No. Move the slide down here. And just help you guys visualize electron domains for a second. So if I give you 2 examples like this, we'll just do methane. Methane's a popular one because it's nice and easy to draw. And then ammonia. You look and you say with methane, okay, how many sides of methane are covered by valence electrons? Well, you have 1, 2, 3, 4 domains. So you have 4 bonded pairs, no lone pairs. In ammonia, you have 1, 2, 3. That lone pair counts as another domain. So it's also 4 domains. Well, how about formaldehyde? We're only going to worry about the carbon here. So if we worry about the carbon, well, we have 1 domain here, 2nd domain there, then that's your 3rd domain. You're only 3 domains around that carbon. think about it, this side is empty. So there are only 3 domains present in that molecule. And that'll affect the overall shape. So the big shape that we learned about today was this tetrahedral shape. And this is the shape around an atom. Missing a word there. Around an atom that is bonded to 4 other atoms. And this is the shape of a methane molecule. Bonded to 4 other atoms, or has, we'll leave that here for now. Never mind that for now. So an atom that is bonded to 4 other atoms, and it's the shape of methane like I just showed you. And the electron domain describes the area occupied by a set of electrons in a bond or a lone pair. Where I wanted to come back to with that tetrahedral shape. We're going to talk about the arrangement of a molecule shape in 2 ways. And this is where this process gets slightly more confusing. One is the electron pair geometry, or the electron domain geometry. And this is the shape according to total number of domains, including lone pairs. Now, its real shape, that is the worst spelling of shape I've ever seen. Or the molecular geometry is based off the electron domain, but it's the shape made just by the atoms with lone pairs invisible. They're still there pushing. They're still there repelling. Those lone pairs, the effect of them on the shape has not changed, but they are now invisible. And so let's look at some examples of this so we can hopefully understand it a little better. So today, the molecules you created had a different number of atoms, but they all had 4 electron domains. So if we look at methane, 1, 2, 3, 4 domains. The electron domain geometry, or the electron domains, are the same as in ammonia, which has 3 bonds and 1 lone pair. Water has 2 bonds and 2 lone pairs. So all of these have 4 domains. So the electron pair geometry, or the electron domain geometry, is the same. We'll call that EPG, is the same, but the shape is different. And the shape is different because of the lone pairs. Right? Again, all of them have 4 domains. So they start in that base tetrahedral form. But now, if you look at the shape of methane, well, you're no longer talking about this lone pair, but that lone pair is still pushing. So you see how methane and ammonia have a different shape. With water, it's the same thing. Those lone pairs are still pushing, but they're quote-unquote invisible. So instead of being a straight line, water is bent. So most of the time, the models you'll use don't include lone pairs. The shape assumes that the pairs are invisible, but they're still influencing the shape. So these are the first sets of shapes that you'll need to know. We have tetrahedral, pyramidal, or you can call it, if my pen works. Hold on a second. You can call it tripod, if you would like. All right, pen, don't fail me now. It's on a little bit of a lag. All right. So this is the tripod shape, if you want to call it that. Next one over is bent. Then it's linear and point. We really don't talk about points. Those are just individual atoms. So really, you need to come away from today with three shapes. That tetrahedral shape, which is an atom, 4 atoms coming off of it. The pyramidal shape, and this is the shape around an atom with 1 lone pair of electrons and 3 bonds. This is ammonia. And then the bent shape, and it's a shape around an atom with 2 bonds and 2 lone pairs, and this is characteristic of a water molecule. So again, pause the video if you need to take some time to copy this down. I'm going to move on. So wrapping up. How do electrons affect the shape of a molecule? Well, electron domains represent the space occupied by bonded electrons or a lone pair. And they're located as far apart from one another as possible. They're pushing. Remember, electrons have a negative charge. Negative charges don't want to be close to one another. Opposites attract, likes repel. So they're going to push until they're as far away as possible. And the three-dimensional shape of a molecule is determined by the valence electrons, both bonding and lone pairs.